Okay, so I'm going to give you guys a concept of curl. Okay? So I promise this will feel familiar. So let me define this, I suppose. So the curl of a two-dimensional vector field F, which is made of P comma Q, right? You guys all with me on that?
Yep. We're about to use this P, Q, Q.
Right, so F is a vector valued function of x and y, right? And then P and Q are functions of x and y, scalar functions. Yes? Maybe?
Yeah, kind of.
Okay, those are the P and Q from Green's, right? Okay, so what's the integrand in Green's? Oops.
Oh, that's the
Yes.
dq dx?
Partial of Q with respect to x
Minus partial Q.
minus partial of P with respect to y. That thing's the curl. You guys cool with that?
Looks very familiar.
Yep.
Yeah, I'm just calling this thing the curl for a good reason. So the good reason I have for calling that thing curl okay, Green's, right, turns an integral around a boundary curve into an integral over an area, right? You guys remember that?
Yeah.
That integral around the boundary curve is the amount of work that gets done by the vector field to push you along this curve, right? You guys all remember that? So when I kind of think Green's at this, I have this vector, this vector line integral, right? I have f dr that I'm integrating, and I get some kind of area integral.
Can you write that?
Up there.
Or move the monitor.
Oh yeah, why is the monitor even?
Better.
How about that? Okay, and then the thing here I'm integrating is, now I'm calling the curl of the vector field F. You guys with me on that?
Okay.
Okay, so I've kind of restated Green's theorem with this new word curl. And now my claim is that there's a good reason for that. So I'm adding up over this whole area here, right? Some quantity, and apparently that quantity gives me the work that gets done by the vector field to go around this boundary curve, right? You guys see that?
Mm-hmm.
So my claim is that the thing I'm adding up is kind of the rate at which little tiny paddle wheels would turn. You guys see all my little tiny paddle wheels there?
Or in this case, spiders.
Right, so
Spiders.
the little paddle wheels are going to tend to turn, right, in this vector field. That vector field, right, being the curl of F. You guys see that? So in my vector field F, there's some tendency for these little paddle wheels to turn. The amount they're going to turn is going to be given by the curl of F. You guys see that's a scalar thing? So that's just the rate at which each little infinitesimal paddle wheel is turning. Some of them turn clockwise, right? That's this way. Some of them turn counterclockwise. If I add those up, that's going to tend to give me the counterclockwise turning of this whole jigger, right? So all see that? And that's going to give me the amount that I get helped along this curve. So that's why we're calling this a curl, because it's literally the tendency of the vector field to curl locally. You guys cool with that? Now, why this exact computation gives you that, I'm not going into right now. But that's what I'm telling you. You guys cool with that? Kind of, sort of, maybe? Okay. So My claim is there's also a three-dimensional version of this, which I have to get out of somewhere. Okay? So, I'm going to kind of set this here. The way you get 3D curl is you take this vector, which isn't actually a vector, right? Yeah, I'm kind of taking the idea of taking a gradient, and I'm going to cross it with the vector field that I'm looking at.
For the gradient of what?
Yeah, good.
Idea. You graded an idea.
Yeah, it's not the gradient of anything, it's the idea of a gradient. You guys with me on that? Cool.
Not exactly. I mean, keep going.
Good talk. So, the way I would execute this is I would make, it's a cross product, right? So I'm going to make a 3 by 3 matrix. And when you take a cross product of two vectors, what goes in the top line?
IJK.
IJK. So you put your I, J, and your K in the top line. Okay, what would go in the middle line is this first vector, right? Which I'm confused about for a second. What goes in the bottom?
F of
Just the vector to a P.
Yeah, the vector field, it's components, right? You guys see that? In the bottom line, I should put the components of the vector field. So that would be like F1, F2, and F3. Or you could maybe think Fx, Fy, and Fz, right? Or P, Q, and R maybe. You guys cool with that? And then into this middle row goes the idea of a gradient. Partial with respect to x, partial with respect to y, and partial with respect to z. Is all good with that? Yeah, which is kind of a bear, right? You guys see this? So if you go through and actually execute this thing, what category of object am I going to get?
a vector because of IJK.
Yeah, I'm going to get a vector, right? Not a scalar quantity. The fact that it's a scalar quantity is because I was working in 2 dimensions over there. In 3 dimensions, this is going to be a vector quantity, and you're going to have to think harder. Yeah, it's cool. That those paddle wheels don't have quite the same interpretation in 3 dimensions, right? Because there's not just like, oh, they spin clockwise or counterclockwise, right? They can spin like this way, or like this way, or like that way, right? So I have to keep track of 2 things. I have to keep track of which way that little paddle wheel points and how fast it's turning. Right? That's a magnitude and a direction, so I should be getting a vector. You guys see that? Okay, out of this, you would get what? Like,
Let's see, I of,
okay, so you get in the I slot,
oh, you get
FC
partial of FC over partial Y.
okay, so you get the partial of the z function with respect to y. You guys all see that? And then,
Partial Y function with respect to Z.
y function with respect to z. Minus j, if that's supposed to be a j, times,
Partial FC times partial.
partial of fc with respect to x, minus the partial fx with respect to z. Oops. And then I need a plus k. And you guys are all muttering, this is a pain in the ass to compute, right? And it totally is. 3-dimensional curl is always a pain in the ass to compute. And what's your last one here?
versus partial of what? Partial of fy with respect to x.
So you get fy with respect to x minus the partial of fx with respect to y. That one look familiar? Should.
Yeah.
What's that last thing?
2D curl.
Yeah, that last thing is 2D curl, right? We'll see that.
No, no. You're blocking me.
So it's the partial of the y component with respect to x minus the partial of the x component with respect to y, right? So this guy at least is something I recognize. That's 2D curl.
So those
And-
are just the curls for each of the planes, right?
Yeah, so these are kind of each of the planes curls. Okay, so that.
Yeah.
Okay, so we'll see why this shows up in greens when we get to Stokes. Cool. But for right now, what I want you to know is there is a 3D version of curl, and you compute it this way. You just take the gradient and cross it with the vector field you're talking about. Okay, good with this? Not really with the idea of having to compute these, but with the x. No. Okay. Put this part in your head. Cool? And put this part in your head. Because there's a cool thing.